Everybody, I've put together a modified heart assignment for you guys. So check Blackboard because I've actually updated the assignment and then also put forward the sample files that you can use to actually be able to generate your data. So here's what we're looking at. I'm going to start off with figure 1 here. And some of this analysis you can go through more slowly in some of the links that I provided before. But I just wanted to make some kind of connections for you guys and what we're actually doing since we didn't actually conduct the experiments to capture this data. So for figure 1, the main thing that they're trying to do is to talk about the connection between an ECG and the mechanics of the heart. And so in the experiments, what we did is we basically put together the frog, put electrodes placed on the arms and legs of the frog, and then we're able to monitor the ECG or electrical activity that was emerging here. The biggest peaks that you see, like this one right here, for example, represents the R wave. And then the rest of these represent some of the other waves that you can typically see in an ECG. The R wave, as you may know, represents the depolarization of the ventricle. And so when looking at the latency between the onset of the R wave, which is the depolarization of that cardiac tissue, to when you actually see that muscular contraction occurring, what you're looking for basically is the difference between the onset of that R wave, which I'm depicting right here, and then the onset of contraction, which I'm going to put right around here. Obviously, that's pretty small, what I've shown you right there, so let's zoom in a little bit so we can see it better, reset some of these different parameters, and we can start to see this kind of difference a little better. So it's really quite small. T2 minus T1 in this case is looking at around 56 milliseconds or so. But you can see how it's starting. That's electrical depolarization happening here. Mechanical event, that onset is right there. So that's the main idea that they wanted to get out of this. That you're actually going to use this file to be able to create two different figures, figures 1 and 2, to be able to help illustrate some of the major points here. One of the most common mistakes is talking about the contraction phase here, which is the systolic phase. That's actually that's not a common mistake. The biggest common mistake is measuring of the diastolic phase, which goes from the very peak of the systolic phase here to when we enter into the relaxation phase, and then the onset of the next systolic phase right over here. So it's this difference right here. It's not when this peak actually ends down here. It's at the start of the next peak. So the diastolic phase can be extended, and we'll find that in the case of pilocarpine and other drugs where it actually gets extended rather remarkably. Okay, so let's go back to our rubric then and try to make, so figures 1 and 2 are all working from that file that we have. Figure 3 is looking at the addition of a drug, and in this case I simplified it so that it's focusing on the parasympathetic agonist pilocarpine. And so the graphs you'll be making and so on are also going to be in these modified Excel spreadsheets that I'm going to be uploading for you. So what we're going to end up looking at is we're going to work with the file that is right down here, recent files, drug data. Now once that's loaded, what we'll see is that we've got a different looking kind of heart rate here. In this case, it's the smaller peak is representing the action of the atrium contracting, and the larger peak is representing the ventricle contracting. If we cruise over to towards the beginning here, what I would like you to do is be looking at and taking your measurements from right around this 4-minute and 30-second point, or right around in here. And because what's interesting, or I'm sorry, 4 minutes and 3 seconds, right around in here. And so that's just a pre-drug phase. And you can look and place that, for example, if you wanted to measure the strength of the contraction phase, you can look for that major peak. That represents the ventricle there. And so this can show you that the force of the contraction at that point is looking like it's V2 minus V1. It's 0.011 volts there. And then the duration of that contraction phase is T2 minus T1, which is right up here at 208 milliseconds. We're looking only at the myogram down here. We're ignoring the ECG up here. We don't need to worry about that again for any of the other figures that we have. Now, if we look here and we look at this type of thing, one thing that we're also going to be asked about is how long is that diastolic phase and how long is the instantaneous heart rate and so on. So if we look at the instantaneous heart rate, you can place the two cursors from one major peak to the next major peak, and that represents the ventricular contraction here and the ventricular contraction here. We're going to ignore this atrial contraction here. So this represents one cardiac cycle. The time is 1 second, as we can see on T2 minus T1. And so we're going to get about 60 of those per minute, 60 beats per minute approximately for that one. And you can make the calculations to determine what that instantaneous heart rate really is. So by simply taking that number of seconds there, and then considering that that's one beat. And so if one beat takes 1.021 seconds, then you can multiply that by the number of seconds in a minute and convert everything over to beats per minute. Now, if you look over at pilocarpine, what I'm going to do is I'm just going to tell you guys to look and consider a little further on in the pilocarpine. I'm going to make this move almost like a movie, and I want you to look at how those shapes are changing and how the peaks. See how they start to get more extended as a pilocarpine takes a longer and longer period of time to work? What's happening over this 2-minute period, right now we're at like 6 minutes or so, is that the interbeat interval has extended significantly. And that's predominantly because of the relaxation phase has been extended in this with the effective pilocarpine. So this interbeat interval is significantly longer, almost it's 1.33 seconds longer. So we've seen this tremendous amount of increase here compared to what we had before. So that's all well and good, and we're excited about what we're seeing in terms of that. How do we actually bring it and measure it and bring that into our graphs? The graphs that they're going to ask you to do is to figure out what that instantaneous heart rate is at rest. They'll ask you to take several different measurements, which are represented here. And then with pilocarpine, so you can take several different measurements after that drug period. And so those are the ones that you're going to use, and it'll generate an average, a standard deviation, and then a percent change. And these numbers you're going to want to enter in. Percent change you're going to want to actually have to calculate on your own. But the equation's indicated here. It's your post-treatment minus your pre-treatment over your pre-treatment. So times 100. So what it currently is, or post, versus what it was beforehand over what it was beforehand. So that's the concept that you have there. And so I've cleaned up the bar graph that you actually generate. And so you'll end up generating a bar graph that looks something like this. It'll be different. I think it'll actually be a negative number that you'll end up getting, or no, actually it'll be a negative number. So you want to go through and make sure that your calculations for instantaneous heart rate is correct here. But typically the instantaneous heart rate will decrease with pilocarpine. Here it's showing an increase. These are just fake numbers that I put in to just illustrate how the bar graph will work. But you'll want to put in the numbers that you use when you calculate it. Okay, so the second thing that you're going to want to, so that's the drug graph that they want there. We'll return back to that glycoside graph in just a minute. So now we're going to go back though and say, all right, the rest of these questions you can answer. I've modified them so that they're a little more clear for you to be able to answer them more effectively. Figure 4 here is talking about active versus the active tension that's made when you add passive tension and how that reflects the Starling's law of the heart. And so what happened in this experiment is basically that we took the forced transducer and we moved it away from the heart, much like you did from, or moved and pulled the heart, much like you did with the gastrocnemius muscle in the frog skeletal muscle lab. And so what's happening in this case is that you're adding that passive tension, and there is a remarkable kind of an effect that you have in this case. So if we go to this file and look at what happens, what you can see is that, again, we're only looking at the bottom trace here. We're just going to ignore the top trace because we don't need it. And you can see these robust types of contractions that are happening with the ventricles here. And what I'd like you guys to do is when you start actually plotting it, start plotting it at around where it indicates L plus 2 over here, because that's where the data is pretty clean. There is a mistake that they made in an earlier version. So just look at this right here and note it as L plus 2. And then the next one is L plus 3, L plus 4. And they're adding 1 millimeter of tension to this as they move upwards. And you can measure, much like you did for the skeletal muscle, you can measure the height of these peaks to be able to determine how much active tension is actually being generated. In the case of the heart, there's no need for a stimulator to be applied to actually make the contraction occur because the heart stimulates itself. It has those pacemaker cells to initiate it. And so that's what's happening here, is that we can see there's lots of them. You don't need to measure every single peak. Measure 1 or 2 to be able to get the average out of that group, and that will be sufficient. Then you can go through and capture that, and you'll want to go all the way up to where they have L plus, goodness gracious, how high did it go? So take it up to, wow, I'm really impressed. All right, so they took it up to 13. And that's looking, or even more, I think. That's looking pretty crazy as far as trying to get decent measurements out of there. So I'm going to make the call for you guys to stop at L plus 9. And that one looks a little better and a little clean. What's really kind of interesting is that you can see that there's a second smaller peak that's kind of coming up here. That's the atrial contraction that they're detecting. But you'll be measuring the height of the larger peak as much as you possibly can. What you're going to find is really that there is no optimum here, that you're going to start increasing, and that the more passive tension you get, the more active tension you get. This reflects a really unique capacity of the cardiac muscle cells to be able to have a great capacity to respond to passive tension. And so unlike what we see with skeletal muscle, where we can achieve the optimum tension pretty quickly, the way that the cardiac muscles are set up is that they're able to induce more of a calcium type of contraction when they start to get stretched, and they also and that leads to a more forceful contraction. In addition to just the alignment of their actin and myosin fibers when they're in vivo is really far away from the optimum. And so this allows the cardiac muscle cells to have a lot of dynamic range, so that as it takes on a lot of blood, it can have a more forceful contraction to help push the blood out of the heart and into the cardiovascular circuitry. So, all right, let's go back then to our figure that we have here, and they're going to ask you for this X and Y axis, looking at active tension, and they ask for determine the extent of change in the active tension and the instantaneous heart rate. So by determining that extent of change, what you're going to want to do is, I would measure the active tension at the lowest and the highest, so at +2 and +9, and then determine how, what that amount of change is between those two conditions. And then also the instantaneous heart rate, which you can measure from peak to peak. So in this case, measuring the instantaneous heart rate at L plus 9, you place it from this major peak right here to this one right here, and that can give you T2 minus T1 at about 1.16 seconds or so. So that's what you'd see at L9. So you can compare L9 to what you have for L plus 2, and let me know what those differences are. And you can express that as a % difference, and note that in the legend. So you've got that. You've got the axis that you're going to be asked to show passive tension versus the active tension. And so let's take a look at what that would look like here. So in this case, when you're wanting to put in the active and tension versus the passive tension, what you can do is note the passive tension just with your numbers that you measured, 4, 5, 6, etc., all the way down to 9. I'm just going to do it for these 3 numbers here. And then let's say that you noted what the active tension is. You measured 1 or 2 of those peaks to determine what the active tension was. Let's say it was 45, 50, 60, and 78, just for kicks. And then what we can do is highlight. We can say that this is passive and this is active. Highlight these. And then from there go up to where we actually have the charts, and then make a scatter plot, and that can be indicated here. And you can do different types of, probably I would use the actual line one there just to help indicate your active tension that's appearing there as you applied your passive tension. And you'll want to label it appropriately. But that's the main idea that you're going to want to do. You're going to want to do it for all of the ones that you measure. So I'm cutting back on sort of the number of measurements that you have to take. You don't have to take like all 3 of those different types of measurements to determine an average. I think that's kind of overkill for what our purposes are in terms of our learning process here. But I would like you to get a nice, pick one of these to measure to get that active tension. Okay, so now let's go back to our, you've seen that XY axis. You want to address these questions here. And then the next thing that you're going to want to be able to do is just talk about this change that happens when you apply the cardiac glycoside saponin. So the process that saponin works and how it works is that it inhibits the sodium potassium ATPase pump. And that disrupts the sodium concentration gradient such that there's an accumulation of sodium out inside of the cell. It doesn't get cleared out as well as it should. And so the sodium-calcium exchanger doesn't work as well to help get rid of calcium. More calcium ends up inside the cell. And so you should have a stronger response to cardiac glycoside. Well, the only example I could find for us to be able to use is where it didn't work. But we're going to go ahead and use that since that's real data. I'm just going to show you where it is. It's actually the drug data sample that we used for pilocarpine. And if you know, last time that we were talking about this, we looked at pilocarpine in around 4 minutes, and then we went over to 6 minutes or so. But if you looked a little bit longer, you see this thing around here, around 7 minutes, where it's pre-saponin. So I want you to take a measurement of a couple of these here of the major peak that we have here. And by major, I mean the bigger peak, the one that's the longer one. So like, for example, here. And note that V2 minus V1, 0.004 volts, not very big. After saponin treatment, which is indicated right here, then what happens is that we'll want to take a measurement. We would expect this to actually increase. But I don't think it worked very well, and sometimes that's the case with saponin. It's kind of a tricky drug. Okay, it went up just a little bit. If you measure more of them, it may actually stand up, but I think it's either no change or very little that actually occurred. So a couple of things could have explained this, and if you look later, the peaks start to get smaller. But it could be that the saponin was inadequately mixed. It could be that the frog heart was so progressively, it was late in the process of measuring these different drugs. It may just have started to croak. And fatigue, and the tissue may have started to not be able to be responsive to the effects of saponin. So I wouldn't use the term croak. All right, so I think that, from 290 and those, you should be able to answer most of those different types of questions. The only thing I think I didn't really address was when I was talking about figure 3 and these different drugs and how it was actually done. And so in this case, just for your information, what happened was that the frog heart was exposed throughout the entire procedure. And at the time that you're adding different drugs, you're adding the drugs dropwise into the heart and then watching what happens to the effects of it. And so the drugs were affecting and mimicking the action of the autonomic nervous system. So sympathetic-mimetic, which is tough to say, drugs were ones that were mimicking the sympathetic system, and then the ones that were, and then there are other drugs that mimicked the action the of the parasympathetic system, and so that's the type of difference that we're kind of seeing in here, and how that experiment was actually being done. I hope this helps, and I will drop me an email or ask me questions if you have any.